Okay, so this is the second lesson about the vector product. So just to remind you, this is the formula that we saw last time for finding a vector product. So quite complicated to start with. It's there in the formula booklet for you, but there's a nice little method visually that you can use to help you with that. So what does it do? Just to remind you again, it's all to do with being able to find a vector that is mutually perpendicular to two vectors. So let's just see how that works. Here's an original vector in red here. Here's a second one, purple. If I were to find the vector product of those two, it would find me a third vector that's perpendicular to both the red one and the purple one. And that's just the best way of thinking of the vector product. Now then, just to clear something up in terms of the right hand rule here, which is the first, the second finger that you use. The answer to that is that it doesn't matter as long as you go around in the correct order. So if I wanted to find the vector product between the red and the purple one, so the order in which we do those is important, but if we go around clockwise there, then the thumb is going to give us the direction of the vector product. So if you try and do that, looking at the screen there, you kind of have to twist your hand right round to make your first finger point in the direction of the red one, but that should work, and your thumb should be sort of pointing towards you there. Okay, now then, as I hinted, there's an alternative formula for that, and this is how it looks here. So the cross product, or the vector product of two vectors, can be given in this format here. And I'm just going to give you a clue as where this comes from. We're not going to actually derive it, but we're going to have a quick look at that on Autograph. So here we have two vectors, the green one and the yellow one. They don't have to be lying on top of a plane like this, it just visually makes it easier to see, although two vectors is what we need to define a plane. So let's just find the vector product of those two. There it is coming out of the page. Now then, I'm interested in what happens when I change these two vectors here, or in particular the angle between them. So what I'm going to do is I'm going to move this one around, and I just want you to have a look at what you think is happening to the vector product. Okay, so the angle between them there. Well, we can't see it. Is it on the other side? No, it's not. Oh, I wonder where it is. Let's just change that angle a little bit. So as the angle between them gets smaller, what's happening to the vector product? Well, the direction is not changing, is it? It's still perpendicular to both of them. The direction is not changing at all there, but the length of it, the magnitude of it is. Something interesting at that point there, when the two original vectors are at right angles to each other, and look what's happening now. Oh, it's disappeared again when we've got no angle between them. Is it on the other side? No, it's just disappeared. So what's happened there? Let's go back to changing those again. You'll see that when the angle is at 90 degrees, the magnitude of the vector product is at its biggest when the angle is at either 0 or 180 degrees. Then it becomes 0. And there's something very, very interesting about the path that this takes. So I'm just going to run through this for you. What I'd like to do, I'm going to put this at a nice angle there so you can see it. I'm going to run this through, and I just want you to see what happens to the size, the magnitude of this vector product now. Okay, should be something fairly familiar in terms of the shape. Okay, I'll try and run that through again a little bit quicker this time. Okay, that should remind you of something that you've already seen. This might remind you of that even more. Okay, so we've got the unit circle there. We've got the height of this triangle that's representing the sine of the angle, and you'll notice that is exactly the same path that was following. Okay, so that's how that's linked. You can see how the sine of the angle gets into that formula there. So let's just see how this works. What we've got in this second formula then is the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by the sine of the angle between the two. And then all of that is multiplied by a unit vector that is at right angle to those two vectors. Sometimes we call that the normal, and it will be called later on the normal to the plane. Okay, so we've got a magnitude multiplied by a vector that is perpendicular to the two. Okay, so let's just have a look at this table here. What I'd like you to do is consider what the vector product would be for these three angles here, and just to compare that to what you came across previously for the dot or the scalar product, and that's just something worth remembering and thinking about regularly. Now then, if this is our formula for the vector product, then that is quite useful for a certain calculation. You might consider it's useful for finding the angle between two vectors, although I would suggest that using the dot product is a far simpler calculation to use. But the magnitude of this amount of this vector is actually really quite useful. So if you just think for a second what we went through, then this is a magnitude, this is a value, and that's a unit vector. So that's a vector of length 1, and this is a scalar. We're multiplying it by a certain value to give us the vector product. So actually this here is the magnitude of the vector product. That amount there is the magnitude of the vector product. Alright, now then, why is that useful? Well, consider this for a moment. You will remember for a triangle perhaps a formula for finding the area of it. So here's a triangle ABC, an angle between these two lengths BC and CA. Then the area of that triangle is half this length here A times this length here B times by the sine of the angle between them. You might remember that formula. Well, why is that useful? Well, if our magnitude of our vector product gives us this amount here, then that looks fairly similar. Half AB sine C. V is the magnitude of this vector here. So here's the vector V, here's the vector W, here's the angle between the two. The magnitude of this one, the length of this vector, the magnitude of this one, and then the angle between the two. Okay. Well, if I divide that amount by 2, that's exactly the formula that we just had. That's this formula here, isn't it? So to get that, all we've got to do is find the magnitude of the vector product and divide it by 2. Okay, so what we can use the vector product for, therefore, is to find the area of a triangle. So if I've got these two vectors to describe a triangle, and I can find the area of the triangle by finding the vector product, finding the magnitude of it, and then dividing that answer by 2. And then, of course, if you think about what the double of that would be, if you didn't divide the answer by 2, then of course that's going to be a parallelogram. Imagine just there. Okay, so here's a question, finding the area of a parallelogram defined by 2 vectors. So what I'm going to do here is suggest that you pause the video, have a go at that yourselves, and then I'll come back to you with the answer. Okay, so you should have found the cross product of those two. This is the answer I got, minus 1357. Did you check that that answer there, using the dot product with one of the previous ones, gave a value of 0? If you do it with 1, that's probably enough to show that's what shows it's a right angle for one of them, and you've probably not made a mistake. What we need to do now, if we want to find the area of a parallelogram, is to work out the value of the magnitude of this cross product. So obviously Pythagoras' theorem for that vector. So that gives us an answer of root 243, which if you can round it to 3 significant figures is 15.6. Okay, what I'm interested in now is looking at some of the properties of the vector product. And before we do that, we're going to hint at some of these by trying to discover some very, very simple ones with the unit vectors. So we're talking about I, J and K. So if we set ourselves up a little diagram to visualize that, I'm talking about unit vectors I, J and K being one unit in the X, the Y and the Z direction. Now which way you choose doesn't matter here, as long as you are consistent when you're doing it. And we need to remember some of the properties we found before when we had looked at that autograph file, and we're also going to use the right hand rule. Okay, so first of all, I want to have an idea of what I cross I is. Now I cross I, that's going to be two vectors that have got an angle of 0 degrees between them. So as we saw before with autograph, when the angle between them is 0, then the magnitude of that vector product is 0. So if the magnitude is 0, then the vector product is 0 in itself. Well, that's going to be the same, isn't it, for J cross J, and therefore K cross K. Now that's simple enough. What about some of these others? So what about A cross J? Alright, so this is where you're going to get your right hand rule out. So let's just consider that for a moment. Okay, so here's our hand. So I and J are your first and second vectors. So I'm making I, or my first finger, point in the direction of I. So point your right hand and your first finger off to the right hand side of the screen there. Your second finger should be pointing in the direction of J. So I'm kind of twisting that down now. So I've got my first finger pointing to the right, my second finger pointing towards me, and the position I've got now with my thumb, which is the direction of the vector product, is going towards the floor. So that suggests to me that that's in this direction down here, which is minus K. The magnitude of this is 1, the magnitude of this is 1, then the vector products are going to have a magnitude of 1 as well. So I cross J is going to have a vector value of minus K. Right, you do the same for the others, so do the same thing for J cross I, J cross K, and these are the two others as well. Okay, and then once you've done that, you might think of an answer to that. So pause the video and see if you can do those for yourselves. Okay, so some important things you would have found out there. I cross J, as we just said, is minus K. J cross I is K. J cross K is minus I. K cross J is I. And I cross K is J, and K cross I is minus J. So the obvious thing that you should have noticed there, that the order in which you multiply these together, the vector product, does have a difference. And we saw that, didn't we, when we looked at the angle, or the order in which we took the two vectors with autograph. And what we notice is that just the sign changes. So we might make a conjecture that A cross B is going to be a negative B cross important property. We also would have seen, or we've got three examples, and we might make a conjecture that A cross A is equal to 0. Because the angle between the two vectors is 0, then the vector product is going to be 0 as well. So let's just have a look quickly at three important properties of the vector product. So just as we've seen there, that it's not at all commutative, so A cross B is not equal to B cross A. In fact, it's anti-commutative, it's the negative of B cross A. So that's an important rule to remember, don't make any assumptions about that. However, the magnitude of it is going to be the same, so A cross B is going to have exactly the same magnitude of minus B cross A. So that's the first property to try and remember, not in the formula booklet by the way. Second one here, it's not associative either, so A cross B cross C is not going to be the same as A cross B cross C, and I'd invite you to check that for a specific case. And the final property is the distributive law, and in fact this is true, it is distributive, the vector product is distributive. So A cross B plus C, so here we're adding two vectors together. If you work out the vector product of that addition, then it is the same as A cross B added to A cross C. That's an important rule, so the distributive rule is true. Now then, we're going to just use that with a couple of examples here, and then I'll leave you. So here we go. What we've got to do in this example here is simplify these three cases. So here we've got A cross A plus B. So there we have an example of the distributive law. So we can rewrite that as A cross A plus A cross B. It's using the previous rule that we just seen there. Now then, can we do anything with that? Well, we can, because A cross A is equal to 0. So that can be simplified to A cross B. Right, second one. Again, it looks like the distributive law. Let's try that out. So A, going to have A cross A here for that. Then we've got A cross B. I'm being careful with the order here. Here I've got B cross A, remembering that the order is important. And then the last one I've got B cross B. Now then, as we've seen, A cross A is 0, B cross B is 0 as well. So the angle between them is 0, so that's going to have a product of 0. And then the ones in between, well, A cross B is not the same as B cross A. In fact, A cross B is the same as the negative of B cross A, or if you like, B cross A is the negative of A cross B. So we've got A cross B, subtract A cross B, so we're left with a value of 0 for that. And let's just try and do the last one. So we'll try and explain this with a few words and a diagram. So let's imagine that I've got a vector A. Put that on the plane, might make it a little bit easier to see. And I've got another vector B. And if I find the cross product of those two vectors, then it's going to give me a vector that is perpendicular to the two vectors. So it's perpendicular to A and also to B as well. Now then, what I have is another vector that is 2A. So it's exactly the same direction as A, but it's twice the magnitude. And the key thing is then obviously A cross B is going to be perpendicular to 2A as well. Now if you've got two vectors that are perpendicular to each other, then the dot product is going to be equal to 0. So that answer there is C. Okay. One last one. I'm going to invite you to try and do these yourselves. What you've got to try and prove in this example is quite similar in a way, is that the dot product of A and A cross B is the same as the dot product of B and A cross B